Imagine if every time you sent a text, it went to a random person instead of your friend. Imagine you're texting your friend about your boss and you're like, this guy's a freaking idiot, and then your boss gets it. Well, that would be chaotic, right? That, my friend, is what the internet would be like without IP addressing. Let's find out how it keeps everything in order. So in the digital world, IP addresses are like phone numbers for devices. They ensure data, like your text messages, gets to the right place. Without them, the internet would be a mess of misdirected information. So how did this all start? Back in the 1970s, the US Department of Defense was working on a project called ARPANET, one of the first networks to connect computers across long distances. The goal was to let computers talk to each other even if they were on different networks. That's when two legends, Vint Cerf and Bob Kahn, developed TCP/IP, the backbone of the modern network. IP addressing was a huge part of that breakthrough. In 1981, we got IPv4, the first widely used version. IPv4 uses 32-bit addresses, which means it can support about 4.3 billion unique addresses. Back then, that seemed like more than enough. But fast forward to today, with billions of devices connected to the internet, we're running out of IPv4 addresses. That's why in the late 1990s, IPv6 was introduced. IPv6 uses 128-bit addresses, giving us a ridiculous number of possible addresses. 340 undecillion to be exact. That's a 3 followed by 38 zeros. It's enough to give every grain of sand on Earth its own IP address, and then some. Now, what exactly is an IP address? It's a unique identifier for a device on a network, like a phone number that tells data where to go. In the OSI model we talked about last time, IP addressing operates at the network layer, or layer 3. This is where routers use IP addresses to figure out the best path for your data. But not all IP addresses are the same. Some are public, meaning they're unique across the entire internet, like your home's street address. Others are private, used only within local networks, like your apartment number in a building. If you've ever logged into your router, you've probably seen a private IP like 192.168.0.1.1.1, something like that, or something that starts with a 10. These are reserved for internal use. These are private addresses. So how do devices with private IPs connect to the outside world? That's where network address translation, or NAT, comes into play. NAT is a trick your router uses to take all of your private IPs in your home, like your phone, laptop, and TV, and bundle them under one public IP when they connect to the internet. It's like your whole family sharing one phone number for outgoing calls. This helps stretch those IPv4 addresses further. Now, let's talk about organizing these addresses. That's where subnets come in. Imagine a huge apartment building with hundreds of residents. If all their mail got dumped into one big pile, it'd be chaos. Instead, you divide the building into floors, floor 1, floor 2, and so on. Subnets do the same thing. They split a large network into smaller, much more manageable chunks. Each subnet has its own range of IP addresses, and devices on the same subnet can talk directly with each other, like neighbors chatting over the fence. Anybody else see Home Improvement? But what if you need to send data to a device on a different subnet? That's where the default gateway steps in. Think of the default gateway as the post office of your network. It's usually a router that connects your subnet to other networks like the internet. When your device wants to send data outside its subnet, it hands it to the default gateway, which forwards it to the right place. Let me give you a real world example. Say you're on your home Wi-Fi, your laptop, phone, TV, dishwasher, they all have IPs like 192.168.1.10, 192.168.1.11, and 192.168.1.12. They're on the same subnet. They can share files or stream to each other directly. But when you want to watch Netflix or me on YouTube, that server is not on your subnet. So your laptop sends a request to the router, the default gateway, which connects to the internet and gets your show streaming. Hi there. Before we move on, let's answer that question from the last time about the OSI model. I asked you to figure out why your video might be buffering. Was it the physical layer with a shaky Wi-Fi signal, or transport layer dropping packets? Well, it could be either, or both. All two of them. If your Wi-Fi signal is weak, that's the physical layer having an issue. Your data is struggling to get through, like a car stuck in the mud. But if the transport layer is dropping packets due to congestion, well, that's the layer 4, the mail getting lost in transit. And shout out to anybody that might get this right before watching this video. All right, back to IP addressing. Devices can get their IP addresses in two ways, statically or dynamically. A static IP is a manually assigned IP address that never changes, like for a printer that everyone needs to find at the same address. Dynamic IPs are assigned automatically by a DHCP server. I did a video early on about the DHCP and how that works. It's going to be around here somewhere or linked in the description. DHCP stands for Dynamic Host Configuration Protocol, which when you connect to Wi-Fi at a cafe, DHCP gives your phone an IP address on the spot. Now let's tie this all together. IP addressing is how devices get their unique IDs to communicate across networks. Subnets organize those addresses into smaller groups for efficiency, and default gateways connect those groups to the outside world. It all happens at the network layer of the OSI model, working with other layers to get other data where it needs to go. So, what do you think is the biggest challenge in switching from IPv4 to IPv6? Drop your comments below. I'd love to hear what you come up with. That's it for today. If you enjoyed this video, please smash that like button, subscribe, ring the bell so you don't miss any of my videos coming up. I'm going to be covering a lot of CCNA stuff. It's not exactly a class, but I'm going to create a playlist, and my goal is to eventually have videos available that will get you to be able to pass the CompTIA or the CCNA. So thanks for hanging out with me. I'll catch you in the next one. Have a good one.